Hey, Tina and Phil, can you guys hear me? Just checking to see my audio working.
Yes, but
Oh, okay, thanks.
hey, Tian, are you gonna open or you wanna do? Hey, but is this the first time you attend?
Second time. I attended live before, right?
Okay,
Second time. Yeah. First time for online, yes, because I'm in Japan. Last time I was in the UIT.
okay.
Dave on? Or let's see. Let me see.
I don't think Dave is it. Today. Vũ, are you the master Zoom master?
I think so, but I am not the co-host right now. I'm asking him to promote me to co-host.
Tian. Let me see if I can assign you co-host. Or Tian, are you there? Can you assign co-host to Vũ as well? I cannot assign. Okay, it looks like it's 9 o'clock. Yeah, Tian, are you up? Only Tian can assign you as a co-host.
Yeah, I think Tin started. He has to assign. There's
Yeah.
two. Tin, you in there twice.
No, I just
No, actually,
one, I
no.
think.
Actually, no. I misread.
Yeah.
Yeah,
So
you
Tian,
started, so
can
you
you
need to.
assign? Can you assign Vũ and Bat as co-host? So I can
Let
have.
me see.
I think you just need to assign Vo because I'm blocking from Vietnam. I'm not sure how that impacts, so I wouldn't do it for me. I'd do it for Vo only because I remember Dave saying something, the two different things. It may cause issue. So I'm a physical in Vietnam, so Zoom knows where I'm coming from. So I think just safely just say
Okay.
Vo
So
only.
I'll make Wu co-host then.
Yeah.
Yeah. So Tian, are you gonna open or you want me to open?
No, you go first. We
Okay.
just do the normal way. Yeah, you start with the
Okay.
lecture and then yeah we do the lab.
Okay. So since we have a lot, so let me start by sharing the screen. And I want to share the screen too. Ok, chào mọi người. Thì bây giờ là mình bắt đầu nhé. Thì chắc là mỗi mỗi tuần là có thể là họp riêng với lại các TA để mà coi thử trong lớp nó có vấn đề gì. Và mình có thể là có thể là TA đại diện từng vùng có thể là đưa vấn đề hoặc là đặt câu hỏi chung cho cái nhóm sau này, nhưng mà mình mới bắt đầu để mình bắt đầu vào trong cái lecture cho nó nhanh để mình qua cái phần mà gọi là thực hành nhanh càng tốt. Thì cảm ơn mọi người đã tham gia làm cái pre-assessment này. Là bây giờ mình có 59 người, thì 59 người trong số 59 người trong số 66 người ở trong cái assignment. Thì kỳ này là mình có điểm, thì điểm để cho mình biết, thì nói chung thì trung bình là cỡ 100 điểm trên 150. Và đây là những những cái điểm total point distribution. Thì nó cũng có một số câu hỏi mà cũng ít người trả lời, tức là nhỏ hơn 50% có đúng, thì mình có thể là mình đi ngang qua những câu hỏi đó nhanh để mình biết những câu hỏi đó là gì thôi, rồi dựa trên những cái này là mình sẽ là làm nói chuyện cover trong cái lecture như thế nào. Thì nói chung là những câu hỏi là câu hỏi do we need to do if compilations errors are reported, thì cũng có nhiều người nói nó không sai, nhưng mà đúng ra là khi mà mình bắt đầu vô, mà khi mà mình cái netlist mà nó không có chạy là mình không có thể nào sửa được, mà mình đưa lại cho người làm synthesis người ta sửa. Đó là cái câu trả lời đúng. Và câu trả lời thứ hai là mình làm gì, những cái physical abstract là có những gì. Thì cái physical abstract là coi như là cái mô hình cho cái place around thì nó chỉ có metal thôi, chứ nó không categorization là nó simulate thì nó không có đúng. Chỉ có via không cũng không đúng, và chỉ có abstraction không thì cũng không đúng. Thì cái đó là mọi người, cái này rất căn bản, mọi người cần phải ôn lại để mà biết. Rồi còn câu này là cái nào là không có đúng cho cái physical abstract. Thì còn ở trong này physical abstract có thể là có metal 2, cũng có thể nó không có diffusion cũng đúng, và nó có thể có metal 1, nhưng mà nó có thể có transistor thì không đúng. Abstract nó không có cái thiết bị device gì trong đó.
Recording in progress.
Ok, rồi SDC là stand for gì thì nó lại có hai thứ, là một là standard design constraint, hai là synopsis design constraint. Nó không phải là một design construct. Còn two timing art là nó là delay art và constraint art. Mọi người ôn lại cái này. Set up a whole không phải, mấy cái kia không phải. Thì nếu mà ai không có cái gì mà không cần phải giải thích thì xin vui lòng nêu lên câu hỏi, còn không thôi thì ôn lại những cái video mà đã có. Còn chip I/O pad cells là đặt chỗ bằng cách nào, thì một là cái I/O placement file là đúng, cũng có nhiều lúc là mình phải đặt bằng tay, và cũng có nhiều lúc mình phải viết cái script, thì tất cả đều đúng hết. Rồi multi-cycle path là gì? Multi-cycle path là coi như là mình có cái timing, nhưng mà mình không cần phải một cái cycle, mình có thể là extend ra multiple cycle, thì câu thứ nhì là đúng, còn những cái câu khác là nó không có đúng. Câu cuối cùng là mình cần go over là cái gì? Oops, sorry. Câu cuối cùng là design meets all timing constraint là khi mà slack là positive, cái slack negative là không có meet timing. Còn path define là không đúng, mà clock không đúng. Thì nói chung là cũng thấy là cũng cảm ơn mọi người đã tham gia, nhưng không biết những cái số còn lại không tham gia là vì không có đi vào được cái lecture này hay không. Thì lát nữa xong lecture là giữa lecture với lab á, thì khi mà mình nghỉ á, thì những ai mà có vấn đề mà làm lecture này á, thì xin vui lòng cho biết. Cho người mà hướng dẫn mỗi miền là đại diện để mà cho chúng tôi biết, để chúng tôi sửa. Nói chung là có thêm cái này, nó có những cái người hình như nó có cái, nó có những người mà làm giỏi, hình như mấy này là những người làm giỏi. Có Trần Hữu Phúc là 125 điểm trên 50, Ngô Quốc Thái làm trên 100, 120, Trần Tấn Đại, có những người làm rất là giỏi. Nguyễn Văn Long, Ngô Trình Khiêm 130, Nguyễn Nam Hải. Và tôi thấy những cái người mà 120, có người Nguyễn Ngọc Huy 145. Như nhiều người thì có những câu hỏi thì hơi mờ mờ, tuy người ta làm 125 hoặc 100, nhưng mà những cái câu hỏi người ta trả lời không đúng thì nó cũng dễ hiểu. 135 rất là ok, chỉ có vậy thôi. Cảm ơn mọi người rất nhiều. Thì không biết có ai có câu hỏi gì về cái bài assessment này không, còn không thì mình sẽ đi vào trong lecture. Ok, mọi người thấy screen thứ 3 rồi phải không ta?
No, still the first one of you.
Ok. Nhưng mà thấy cái screen rồi đúng không?
Yes.
Okay. So hello. Today we'll discuss the design import. Right? This is the first step of the place and route flow, and which involves import, floor plan, place, CTS, route, and export. Okay. So let's start with the review overview. So the main input is the gate level netlist, right? And this gate level netlist was created from synthesis, and we use a command called read netlist to read it in. And then in this gate netlist, we have different building blocks, namely standard cells, macros, and IO path cells. And to map the physical to the netlist, we read in what we call physical library that includes all these abstracts. So we use a command called read physical to read in. And these cells also have, in addition to the physical libraries, they have a timing libraries that comes in the .lib format, and all the timing constraints need to be read in. Sorry for this. So what we call an MMMC, a multi-mode, multi-corner file that calls the SDC, the constraint files, and also include all these .libs in the set of timing constraints that are used to drive the timing of the chip. And then in addition, we have what we call physical constraints that have the constraints on the shape of the chip. For example, die size, the width, and the height, if there are any constraints related to that. But there will be a file called IO placement file. This placement file places the IO pad onto the rings, and we'll go over how that is done. And lastly, we have the technology file that contains the layout rules, and also that contains the extraction, the RC extraction technology files used to extract the RC on the wirings. And the physical constraints and the tech files will be read in, with the command called init design, and the MMMC is read in using a command called read MMMC. So that's an overview. So after all the inputs are read in, then we do some sanity check by checking the quality of inputs by running a few commands to make sure that all inputs are valid and that constraints are accurate and complete. After that, we say the design is ready for the next step, which is the floor planning step. So to go a little bit in further details, because of the flipped classroom, I'm not going to go over a lot of details like before, saving the time for practical. So just touch on the next level. So the netlist import is going to be at the gate level. And the gate level is structural, meaning the building blocks are cells, they we call leaf cells, and macros. So quickly, a leaf cell is the primitive cells, which are like AND and ORs, inverter, flip-flops, etc. Macros are still the last level of details, meaning it is a block at the place and route level, but it is a more complex building block and may contain the leaf cells underneath. So just quickly about that. And the file format is Verilog. So mainly Verilog, even though in the past, or maybe still certain design is described in VHDL. And the netlist come from logic synthesis, as you know. And just a quick recap, logic synthesis is the step that we take to transform the level transfer, registered transfer level abstraction into a structural abstraction that you see gates. These are mapped at this time after synthesis are mapped into the technology, say, 22 nanometer or something, but they meet the timing coming out of this, but they have a few things that are really different from place and route, meaning the clocks are ideal. The skews on the clocks, you will learn what they are estimated, and then the wiring parasitics are estimated or calculated still on an estimation basis. So just quickly on the synthesis. And then the netlist is imported. So the whole import is done via the tool, like, Innoverse, right? So it can be read, the netlist can be read in using a read netlist command. So that's the netlist import. And then cell abstract are imported. The cell abstracts, just to review, what are the cells in place and route? The cells in place and route are the same as the cells in synthesis, meaning standard cells, memories, and other IPs. But in addition, they might have physical only cells that are applicable, are needed in place and route in the physical world and not used in the synthesis world. So learn what they are. So the at this step, we read in what we call the left file, which is a human readable text format for library exchange format. And this is a file that describes the physical abstraction of a cell. So just quickly, physical abstraction of a cell is a view of the cell that is higher level, where the details are hidden because they're not needed in place and route. The less data you have, the faster the tool can run. So the layout over here have diffusion, poly, and N-well, etc. When it is in place and route, it only has metals, because at the place and route, we place these cells and we wire them using metals only. So that is the abstract, and it's generated by an abstract generator or some other sources. So yeah, and what are the other sources? As you learn, all these building blocks of foundational IPs or custom IPs that come from either from external IP vendors, so standard cell IO libraries, compilers, hard IPs. They come in, and the abstract view is already built in here. So you just identify where they are and you read them in. Or if the IP is established, designed internally, then the internal team will generate the abstract for you using the abstract tool. So all these that left, what are the formats? There are binary formats that are more efficient and better for modern flow. Are binaries like open access from Cadence or Milky Way from Synopsys. But they all can be read in using the command called read physical. So that's cell abstract. And the next one will be timing constraints. So this is the most complicated and the most important file or set of files that you're going to read in, because this determines everything. This is a constraint in terms of timing. Timing meaning is a chip operating fast enough for the requirements. So it comes out, comes in of a file called MMMC. It stands for multi-mode, multi-corner. And how was it built? It was built mainly by hand by a logic designer, and mainly what in it are the following. You over here is everything's about timing. Timing includes PVT, process, voltage, and temperature corners. As you know, due to variations of the process, variation of voltages, and variation of on-chip temperatures, the delays will be different. So to represent the combination of each, for example, in here say SSH, LS is for library set. SSH means slow, hot. Slow, the two numbers to the two letters are for the N and the P transistors, and hot is for the temperature. So over here is slow, and ignore the G for now. And then 0.81 volt, this is the operating voltage. In this case, the typical voltage is 0.9, so 10% below 0.9 is 0.81. So at this corner, assume that the transistor is receiving the smallest voltage, and the hot at the temperature of 125 C. So this is a corner where the delays through a gate is very large, is max. So you define what are the dot lib, meaning the timing model for that corner, and so on. The next one will be for the fast corner for you to analyze the whole behavior. So that's the first. Use a create library set command. The next one you specify the operating mode. As you know, the chip can operate, or a design can operate in a functional mode, or in a scan mode, test mode, or sleep mode, wherever. So you define those because each mode will have a different constraint. So each mode will have a functional, like a .sdc constraint file associated with it. And it's called constraint mode in this case, functional scan. So you create that. So you create all these different things, and then you combine them later, right? And then the RC corner is just like temperature, just like transistors. The RC have a min and a max, and it also have a temperature dependency. So you feed in, you create a corner, and you say go for unit, for technology unit capacitances and resistors, use the RC words or RC best. R and C's are resistors and capacitor. Worst is the worst, meaning for this case, RC worst mean the combination of R's and C will produce the slowest, the biggest wire delays. And RC best is will result in the fastest wire delays. So this is for max corner, and this is for min corner. So you use this create RC corner, and you call it RC max, RC min. And the next one would be delay corner. Delay corners are just a combination of a library set and a RC corner. In this case, the delay corner max, meaning this corner, all the delays are max, meaning the transistor, the gate delays through the transistor to a gate is a max, and also the wiring delays are max. So this is the slow corner, and the min is a fast, everything fast, including the high voltage and everything. And so that's the delay corner. So all these individual attributes are combined into what we call analysis views. Analysis view is a view that when you run timing analysis, you will use a view to say what the timing looks like in this analysis view in functional mode and maximum delay. So you say, okay, give me the timing report for this maximum delay corner in the functional mode. Or this one, give me a timing analysis in the fast mode where everything runs fast, and in a scan mode min is the minimum delays, right? So these are the example of two extreme corners that if you meet timing on these two, you meet things, you meet timing in areas in between. So what we call a corner analysis, all these boundary conditions, if you meet them, then you guarantee the chip will operate correctly within the range. So these analysis view are important. And then active analysis view is that uses a set analysis view. You say when you check setup time, you use functional max and test max and everything max here. And when you check hold time, you use everything min or fast. So this is how you set active analysis view for each of your analysis. So this is very complicated, and if you make a mistake here and you sign off, the chip, you think the chip will operate correctly, but if you made a mistake here, the silicon come back and it doesn't work as you simulated. So this is extremely important that you understand everything that is in here. So and this file is a TICO file, is an advanced TICO file that really just manually written, like I mentioned, by a synthesis engineer, and this can be read in using a command called read mmc. So so that's a constraint. And finally, on the input, there are physical constraints. So in the synthesis world, there are no power and ground. So everything wasn't connected there in terms of power and ground. But in the place around physical world, you need to know the pin of a cell, VDD, and ground pin of the cells. What net does it connect to? So usually it's the same net like VDD and ground, but sometimes on the chip you can call it VDD core versus VDD IOs, because the IOs will have their own VDD. So when you add a chip, there are multiple VDDs. The simplest form will be the high voltage VDD for the IO paths and the lower voltage VDDs for the core. So you need to be in the netlist. You say if you are a core device, connect the VDD to the VDD core. So that's why you need to provide the net names so that the placement route tool can connect them for you. And also to place the pads and at different locations, you can automate that by providing a placements file where you specify each of the pad. For example, in here, ignore the prefix, but so the pad, the IO MDC is going to be on the top edge of the die. The TXD0 is on the top edge of the die, but next to it. So you're going from left to right. So the leftmost is MDC, the next to it is TXD0, and so on and so forth. So there'll be four edges of the chips. So you say which pad will go on which top, right, bottom, or left, and you use this one to automate the placement of it. But if you working on a block level, then you most likely you just create a TICO script that you define what they call PR boundary, meaning the boundary where you do the placement route inside, and you place all these pins, no longer IO paths, because these are the internal. They're not IO paths like this, but they're internal pins that connected to the remainder of the chip. So you place all these pins and using the TICO script, and that's how you do the block level physical constraints. So oops, sorry. So you can see this init design. So all these things are specified when you set up, and when you run a command called init design, then all these things will be used to place your pad cells. So at the end, after you run all these things and you run a init design, then you will see, and Tian can show you. So you see this kind of view, and in this view, the chip is in the middle, where all the IOs already placed accordingly to the IO placement file, and on the left are your what you call utilization. It's kind of hard to see. It's kind of TU, and Tim can tell you as well. So these is the target utilization based on the cells that coming in. Yes. And on the right, there are macros. These are just hard macros that they're not placed yet, but they're on the side to show you what the sizes and different things are. So this is the database that is ready for the floor planning. Even the IO path, placement is part of floor planning, but the way the flow is set up is done via the import step. But this thing is saved in a database, and you can name this database, but we can call it an import database. So this basically, the design can be ready for the floor planning. However, there are some sanity check that we need to run to make sure that that the design is really valid. Meaning, when you read things in, any error, look for errors. And keep in mind that log file can be very, very big and complicated. So you don't just worry about every detail of it, but you look for keywords and for errors, and you learn it in the lab somehow, hopefully via experience as well. But you check different things, but because of time, I'm not going to go through it. But basically, does an atlas compile correctly? There are different things that you're going to check for, like a uniqueness of the instance name, whether or not you have a black box. A black box means that the incoming netlist doesn't have details on certain module, and it result in black box. So black box is not valid. So you check for those, and you check all the timing constraints that you learn more and more as you go through. At this stage, you just need to know there's some quality control that you need to check for. Are they accurate? Some of them are dropped. Are there things that are not constrained properly? Meaning, are they complete? Because if you don't constrain certain things, then that means that you don't constrain for speed. And if you don't constrain for speed, if they're slow enough, they can break the chip. So, but the thing that you will run at this step that automate the whole thing will be, you run the timing report with 0 RC delays, and why is that necessary? Because if your timing is not met with 0 RCs, meaning in synthesis you have 0 RC, you have estimated RC. RC means wire delays, and you try to meet timing. But if your wire delays are 0 and you still don't meet timing, something wrong with your netlist. So you want to do some sanity check by running that and see if you see any violation for timing. But before that, to check really. At the high level, you can run a couple commands. The first one is called report analysis coverage. So this one will give you the will give you report like untested. What are the percentage untested? You see check type here, clock gating, pulse width, recovery, setup and hold. All these different check types, you see, hey, do they contain all the checks that are necessary for a complete timing constraints? And then you see number of violations, right? If you have 0 here, you have non-zero, then you will look into it, say it better not have any violations because I'm giving it a 0 RC, and maybe some untested here that that really need to be looked at. So having that report analysis coverage, and then there's a check timing command that it will show you inconsistency and completeness, and we're not going to go over those things. But the key, some keywords is WNS and TNS. WNS is worst negative slack, and TNS is total negative slack. So the slack, as you learned earlier, you probably remember, is the amount of the difference between the arrival time and the required time. Meaning you want it for you to meet the timing, you need to have a WNS greater than or equal than 0, and then as the total negative slack is just a total a sum of all the worst case negative slack. So so it is meaningful when you have violations, and by seeing the total negative slack, you see how bad the timing violations are. Meaning that if you have so many negative, you add them up, they have a big number, and if you have only a few negative, then you have a small number. So okay, so the problem is manageable. So what we call report slack histogram. So the slack histogram to tell you what is the slack range and how many of them. For each range, or visually you have here green means passing above 0, and red means negative slack. So you can see here there's a lot of violations up until 2.7 nanosecond of violation. So this one gives you a visual of how bad your timing is. At this point, you're not worried about this yet, but because you only do this sanity check, but it's kind of good to know. And then at this point, you don't need to know about these either, but it's nice to know how to read a report timing. And Tien has a lot of things in the lab that helped you go through this. But this is just a reference for you how to read the path, the beginning of the path, and how the body of the path looks like. So I reserve this time for the practice, so I'm not going to go over it. So that's I think that's pretty much all the checks that we do in the import steps. Reading in, and in summary, you read in the inputs, you check quality of the inputs, and if there are some issues, and you go talk to the synthesis guy, fix it, or you go back to the previous step and try to do different things with the import database. At the end, you say all inputs are valid, all the constraints are accurate and complete. So I'm ready to go to the next step. Why you need to do this? Because if your timing is bad and if your constraints are not complete, you go through this floor planning and go through days of doing all these implementation to find out it's a waste of time. So you do want this step, even though it's simple, but it's critically important. The more you check at this step, the better for you to go through the remainder of the flow. So I think that was it. Do you have any question before we go to the go to the labs step? So as you can tell, my lecture slides changed a little bit, and I don't cover a lot of stuff. So I'm going to update my lecture slides, but there are a lot of backup slides that in the lecture slides that help you understand more deeply about what we cover. Okay. So Tien, are you ready to jump right into the lab? Or what do you think we should do?
I'm going to take 5-minute breaks.
Sure. Okay.
Ok, thì Thiện muốn là mấy trong cái 5-minute break này, nếu được thì mấy TA hoặc là mấy em student á có thể log in trong cái machine á, trong cái 5 minute break này mình có thể làm cái đó luôn. Ok. Rồi khoảng sau 5 phút thì mình bắt đầu làm cái lab.
Ok, với lại mấy cái mà trưởng nhóm TA, nếu mà trong cái quá trình làm lab mà những ngày qua với lại những cái lớp học mà có những cái gì mà nhóm cần hỏi hoặc là cần giải thích thêm ở trong cái buổi học này thì xin vui lòng cho biết. Yeah.
Everyone will be returning to class in about 1 minute.
Hi Dave.
How you doing, Phil?
Good. You situated?
I am on a bus on the way to Halong.
Wow, you don't have to
This
worry
is
about it.
this is science fiction.
I know. Oh my God.
Hey Dave, if you have time, swing by and say hi to the team for me, including NIC. So text me back if you have time. If not, then I won't introduce you.
Yeah, I'm not sure.
Hey,
I'm not sure, but I will let you know as soon as I know. I'm definitely
Yeah.
going to be able to go to Da Nang.
Okay.
Okay. So Tian, I just put a poll because there are 66 assigned and we have 59. So I wanted to have a poll. So
Mhm.
Dave and Wu, it looks like there are 5 people cannot open the assessment. Okay. So there are 7 of people. She said Leo khác.
Are you sharing,
So,
Phil, or no?
Oh, okay. Let me share this here.
I see it. I think you share.
Oh, am I sharing?
Yes.
Does anyone else see it? Or should
don't
I
see
share
it.
the screen? Let me just share the screen.
I don't see it, Phil. I only see the, yeah.
Okay, so this is the I don't know where is it. You read. So the poll is that lý
I
do
just
tôi
see your
không
laptop,
làm
Phil.
laptop.
I mean the laptop display, the screen only. I don't see.
I do see the poll that pop up, right? On title poll 6. I do see it, the poll, but the screen is not sharing. That's all.
Let me share the screen again. So I'm sharing. Let's share the screen number 3. Okay, do you see the poll on top of the
Yeah, see your screen now.
I see the lecture 4, but that's it.
but it's not on top of the screen? That's weird.
And Phil, can you share the poll? Share the screen?
Yeah, let me see if I can do that. Share. I don't see the poll on top of the share. Let me try to share the
Just
screen.
ask the student to see if they can see the poll.
Yeah.
Poll popped up automatically for me.
It does.
Yeah, and
Got
our
TA
5
again.
minutes.
I got
Our
TA
5
again.
minute, yeah, our 5-minute break is over, so the students are waiting on us.
Yeah. Does anyone who can share the poll? I don't know how to share it though. Maybe I just do a screen dump.
I think we have to end the poll to share the results.
Oh, maybe that's what it is. Sorry, share result. My view. Do you see it now?
Yes, we can see it.
Okay. So does it, Tian, you see it?
No, I don't.
Anyway, okay. Why don't we just? So I just read in. There are like 6 people cannot open, and there are 8 people. There's some other reasons. 2 people say no time. 3 people say no knowledge, and 2 people say they don't know if they have to do it. So cho mọi người trong cái poll này có 2 người không biết là cần phải làm, thì bây giờ cũng biết cần phải làm, tại vì cái poll mình cần làm trước khi mình học để mà cho mọi người biết là coi như là cái kiến thức đến đâu, để mà mình có thể dạy cho nó được. Còn mà có những người mà không có mở được thì xin vui lòng liên lạc với lại TS dash yeah, có một cái địa chỉ có thể Vũ với lại hoặc là We can share the địa chỉ, xin vui lòng gửi cái chi tiết về cho Vũ với lại Dave để mà hai người đó có thể giải quyết được. Ok, Thiện, go ahead, Thiện.
Ok, xin chào mọi người. Thì hôm nay mình sẽ làm cái phần 2 của cái lab 2. Phần anh Phil đã nói rồi, thì bây giờ mình sẽ load một cái design rồi mình thao tác trên một vài cái dữ liệu mình có. So let me share my screen here. You guys see my screen yet?
Yeah, yes, David. Let me see your screen.
Okay. So the format of the lab is very similar. So with the part 1. So this is part 2, right? So so the first one here is just I want to show you where how the data gets structured, right? So we have lab 2 import, and underneath we have the database access, lab that optionally you should do. And then last week we did part 1, and today we're gonna do part 2, right? So the way it's kind of like breaking down. So we have the data here. So I kind of like highlight some of these important files that we're gonna go through. So the first one is the MMC. So Phil already mentioned that, but we're gonna go in and see the content within that MMC. We're gonna look at some of the constraint here, just to get familiar with how you create clocks, how do you set timing constraint, and of course you need to have a net list, right? So import those are one of the item in the input is there's a net list, and then the IO placement. So I think Phil already showed that, but we're gonna dig a little bit deeper, open the file up and take a look at it. Here is very similar to part 1. So we have the layout exchange format file, and then we have the timing library, right? So the way you look at this is, one is the lab is the physical definition, right? And then the lib, the timing is at the timing. So we need 2, right? So we need the physical aspect, and then we need timing aspect. So we pull in, and then we take it in the design. And I put together this, import article. So we're gonna look at it as well, to make it really simple. Similarly, the data is in here. I put it under lab 2. So if you did part 1, you want to do it again, to copy the part 2 over, so we can do the lab here. So okay, so the first one we're gonna look at is the import article, right? So I show it here, and I also, if you look over here, so under part 2, we have, let me close this, script import, right? So if I open this up, so it's actually it's very simple, right? All we have here is the top here we say, okay, so we have a power net, code VDD, and then we have a round net code VSS, right? And then the next one, this is even though it's just one line, but this is extremely important, right? Because all of the information that describe your environment, your design, your timing, is in here, right? That's the MMC, right? We're gonna take a look at that later. So this one gonna contain all of those timing information in it. And then the next section is, we read in the physical aspect of it. So in this case, we have all the list of the left file, right? And I think last week we did look at this one. So the top one is extremely important, right? That one has the technology definition in it, right? And then all of these are essentially, you can tell by the name, right? These are the for the path, right, or the I/O, and then we have all the memory, um, and they located in here. So if you want, you can go here, take a look at them again, right? So the first we do the read MMC. That's the timing information. And the second one is we read in the physical data, was contained within the lab file. And then the third one is the connectivity, right? Object design. And that is the netlist, right? And this one is just saying that, yes, you can read in multiple netlists, but then you have to decide, you have to tell the tool which design you want to, make a top design. In this case, we have only one top design, but it was its ASIC entity, right? So after you do all those 3D things, right? The timing, the layout information, and the connectivity, then you say init design, right? Read all these in, combine them together, right? And when you've done that, your design is in the memory, right? And for this case, we say, well, but I want to do something extra, right? So we're gonna create all the I/O ring in this ASIC entity, and then we create a floor plan. So it's just easier for us to look at. So if you look what's back in here, I already did all those for you to save you time. So here, right? So you can see here, I invoke the universe, and then I import, right? The one that we just looked for file. And then so after this, how you source this, and this is what we have here, right? And in this case, right, we can switch between the layout and the physical view, different view that we touched on I think the first week, right? So this one, let me zoom out here a bit. Yeah, so I think Phil did mention about this one, is that this essentially this is what they call a target utilization, right? It's currently calculated as 84%, right? So initially you want to look at that number. If it's too high, then you more likely you want to increase the die size, right? If the number too low, this could be pad limited, then not much you can do. But if it's not pad limited, that means your design is constrained by the pad ring, right? If that not the case, and then you can decrease, make the dice a little bit smaller, right? To, it depends, but usually between 70 and then 80%, right? So it's reasonable. So let's go back here. I think we covered that one, the import. And so we did after we look at it, we actually imported. So let's see what I have here. So in a GUI, change the floor plan view. Oh, okay. So you want to verify the path order and then compare with the IO file, right? So let's do a mini exercise. So what I'm saying is within this, floor plan view here, I'm gonna see, let's say zoom in a corner here, right? So because we just read that import and then, magically all these, IO get placed evenly, right? So if you notice, the space between these pads, you, you know, you can measure them, roughly, they are exactly the same, right? Because that's the default behavior. It's gonna all the pad on the top will be placed evenly, right? And then on the left side here, it's gonna be different because the number of pad are different from the top to the left side, right? So let's see. But let's come back here. So let's look at this, IO file. So where is it? So it's under data, right? So if I open the data here, so we have this here, ASIC entity IO, right? So, okay. So let's see here. So we have global. So that's the syntax, right? You say, let's see the IO pad portion. And I'm looking at the top section, right? So let's see here. So we have MDC. Okay, so that's the first one, MDC, right? I'm going to zoom in a little bit more. And then TXD, right? So it start from the top left and then it's go to the right. So we can just do double check at the end here. Let's see. Yeah, something with the Q underscore N, right? So if I go here, so that's my top portion. You go down to the N, right here, right? So QN. So we verify the top, right? So I'm not gonna do all of it, but I leave that to you. You can do the next or verify all of them. Um, Another thing is when we do a real chip, really, we're not gonna use this. We're not gonna do actually all the pad gonna be evenly spaced, right? That's not realistic, right? So we actually go in and actually determine um, uh, where we want to place the pad, right? So right, but so this exercise is good. Um, yeah, it just look at how many pad and then it just space them out, right? So okay, modify the pad order. Okay, so let me see. Yeah, I think I can do that quickly. So let do something fun. So let's see here. So I'm gonna go to the top again. So right now we have MDC, the top one. So I'm gonna just move it to the second, right? So I say right there. Okay, just want to verify. So right now MDC is still the pad number one, right? And the TXD underscore 0 is the second one. So I just update the ASIC entity.io. Nothing happened yet. So I have to switch back to the universe command here. And then I'm going to say read IO file. And then we say data ASIC NTT.io, right? Let's try that. And let me refresh it. So just as we expected, the order of the path has changed, right? Because we update the text file, we reload the text file. So that's one way you can do, you can make change and you run it over and over until you're happy, right? So we done with number 3. Okay, any questions so far? Let's see here. Okay.
Quý vị học viên nên nhớ là mình đang học hỏi nha, học phải có hỏi nha.
Yeah. Nếu mà dễ quá thì không cần hỏi. Okay, so we're gonna do the next one, number 4 here. So this is very important as well. So we're gonna look at the view definition, right, or the MMC file. So let me switch back to here. So this is under data, right? Part 2 data, view definition. So okay. So if you already cover the lecture, but I just want to touch on a few things here. It's kind of like go backward, right? So this file is more like you do bottom up. You define the lowest structure and then you build on top of it, right? So for me, usually I go and I do it in reverse, right? So if we go to the bottom of the file, and then we say, wow. So essentially, this is as the highest level, right? Is the analysis view, right? So you think of the analysis view is like you have a chip. You want a chip to operate at different you put the chip in a different mode and timing, right? So if you look at this one here, let me see. Okay, so the analysis view, it has essentially two big item, right? The first one is the delay corner, right? So essentially say, wow, how's the timing look like, right? And then what is the mode or the constraint for that, right? So it have two, element, right? Timing, fast or slow, and how it's operate, right? Is that functional or is that scan mode or some special mode, right? So one is the behavior and one is the timing, right? So that's the highest level, right? And then you kind of like, okay, so how you define the delay corner? You go back here, say, oh, create delay corner. So the delay corner have two portion, right? So you have the cell delay, and then you have the RC delay, right? So that's what it's combined here. So you have the timing condition was up here. Essentially, it's just a library set, right? It's just a combination of different library set for a certain corner that you want. In this case, it's like you want to define a corner that all the cell is very slow, right? So that's for the cell. And then the RC is for the interconnect, right? So you have two, again, the delay corner have two pieces of information, right? The cell and the interconnect, right? So, and right here, let's say how you do the RC corner, right? You have all of these, technology, and then you can scale up, scale down right here, right? So, and then for the cell delay, you have to create a library set, right? So you look at the chip design, you have different library, characterized at different, corner, and then you group them together. Say, well, realistically, if I'm in a certain, overrating condition, I want to simulate that. So you pull in all these library cell, and you create that condition, right? You want to simulate that. So, and then that's the you have the timing, and then you have the behavior, right? This is where the constraint mode come in, right? That's where you have right here. So how the chip gonna behave at certain condition, right? So I said here, so we have the create analysis view. That's the highest, and then that one need the delay corner and the constraint mode, right? And then the delay corner, you have the RC corner and the library set. So yeah, you take a look at it, essentially get familiar with it. I think do we have that? Okay, so we do have that. Okay, so let's move on to the next one. Okay, so I want to do just one example here. Is that we have two timing library set in this case. I think we have the create timing set. Create library set. So the first one here we call is fast, right? So we say we're gonna go in order fast library, right? So fast mean that we have minimal delay, right? So in this, timing simulation, the cell is very fast, right? So and I want to look at, we're gonna pull up here the fast.live, and then similarly, we have I think it should be another one here. So this one is slow, right? So we have the slow library. So let pull. I already have it here, but I want to do it live so you can see. So library, we have the left. We look at that. And let me close that. So you can see here under the library, we have the max and mean, right? So essentially max means slow, mean fast, right? So this is where I expect the slow to be in here, right? Slow gonna be under max here. So let me open that up. And then for the min, so I'm gonna do the fast here, right? So I'm gonna do which one I do on the top. Okay, so I'm gonna do the fast on the bottom, just like what we have here, right? So in this exercise, I want to, because it's just so many cells, right? We want to look at the D flip flop here. Just randomly, just pick one. So we have the D flip flop HQX1. X1. Okay, right there. So let me move on top. So I'm gonna do the same here. Okay. So if you look carefully, it's the same cell, right? And because the fast, and say, oh, so what's the difference between fast and slow? So I think in the lecture field you mentioned that essentially we look at so within the library cell it has many pin, right? So we have, because it's a flop, so we have the CK pin. And you have all these information, the input, direction, capacitance, but we want to look at the Q pin, right? So we have D pin. It's all the same, but I think it's more interesting. We look at the output, right? So we have the Q pin here. Okay, so top here, I'm gonna look for pin Q. Okay, so I think this is what I have here as well. So you can see the Q pin is a flop. So yes, direction is output. Max capacitance. Yeah, later on, you know, at the end, we have some DSC check, right? So that's where the max capacitance going to come in. So, and then so the timing. So for this Q pin, they have the timing information, right? They call timing here, and they call related pin. So the way you think of this is CK, the Q pin is related or clocked by the CK, right? That's the timing art, right? And I think Phil already mentioned, so this is the timing table, right? You have the index one, which is the input sleeve, and then the index two is the output load, right? Output, right? So it's like a lookup table. So you have index one go this way, and then index two go that way. So if you look at a cell, you have two number, right? The input sleeve and the output output load. And then you can say, oh, where is it in this table, right? So so you look at the index one here, index two here, they're identical, right? That's how they characterize. And because this is slow, so the different here, let me look at the first one here. The first one here is 266, or almost like 266 picosecond, right? For the same slew and load. For the fast one, it's only 92, right? So essentially it's about 3 times faster, right? So, and this one, the last one is about point 0.8. Let's say 1.9. So it's a little bit more than 2x, right? So it's not going to be linear. So, but that's why you see that's why this is fast and this is slow, right? So, and just so many cell in here. I just hold on, is that cell? Okay, so let me do this. Right, so you can see just so many, right? So yeah, it's like 500 different cell in this library. So we just do like one, right? So you can do more. I mean, the lab is just want to give you get you to start in this journey, and then you can study a lot more. You don't limit by what I put in the lab here. So okay, so that's number 5. Okay, so we have the timing library tell you how fast, how slow certain cell gonna be, right? But then when you design um, your chip, you have to come up with how fast you want to design your chip, right? you go out and say, well, my chip gonna run at 1 gigahertz, right? Right. Another company gonna say, okay, but my chip run at 2 gigahertz, right? So where's that come from? That's so when they design that chip, they have the constraint, right? The target performance, right? So that's the next one we're gonna look at here is the timing constraint. So let's go back here. I think I have to reset my okay. Timing constraint. So look at so we done with this. So go back with the data. So let's look at the view again. Let's see, look at this one. So just review it a little bit. Okay. So in the MMC, we define as create constraint mode, right? And we name it, say, oh, this is a functional. That's the behavior, right? We want to create this functional. And in this case, it's a slow functional, right? And we associate the two things, right? We associate the SDC file, we call it here, right? Slow max top constraint, right? So we're gonna look at that. So slow max top constraint. Slow max top constraint. This one. Okay, so let's look at that. See here. So this is the constraint, right? Top level prime time constraint. Okay. So the most important thing is the clock, right? So because our design is synchronous, right? That means everything is to be clocked by some clock, right? So the first thing you come in here is you can define all the clock in your design, right? So you have like create clock, you have a name of the clock and the period, right? So the two things, the period and then the waveform, right? So in this case, the thing is 50-50, right? The duty cycle. So let's say 40, you have 0 to 20, right? So it rise at 0 and it's fall at half of the cycle, right? So it's 50-50 dual cycle. It doesn't have to be that way, but I think so the symbol design is gonna be like that, right? So 32, 0, 16, right? And actually all of them the same. So by looking at the period, you know which one is fast, which one is slow, right? The one with the higher period or longer duration, that means it's slow, right? So in this case, this one is the fastest clock here, the period 4, right? So these are very important, right? So more likely the one that fast going to constrain your design more, right? Than the one that runs slow, right? So you have more time to do something, right? So, and then, so that's the clock. This clock has the latency, right? Latency is just a simple way is just say, well, it's a delay, right? So, um, yeah, when you learn about the clock tree later on, then you understand the latency more. It just, when we don't have the clock tree, it's just a latency, right? So, and here, yeah, we have the set input delay and then set output delay. So I think one way to look at this one is if you have a chip here. Let's see. Let's go back here. So I believe this is the input pin or input pad, right? So input delay is a constraint, right? So this input gonna come into the design and say, so you need to tell the design when I expect the signal gonna come respect to the clock edge, right? So that's where the set input delay come in is that, yeah. So it's say here, set input delay respect to a certain clock, right? So when that clock rise, I expect my signal to be no later than 4.5 nanosecond or whatever picosecond, whatever the unit is, respect to, for that port, right? So, and then same thing for output. Right. So output. So you need to constrain this. So it's in the outside, right? So that receiver end have to know when your signal gonna come, right? So say, wow, my signal not gonna come, later than 1.5 after the clock, right? Something like that. So
Hey, Tian, can I interrupt? There's
yeah,
a question in the chat room asking 4.500. The unit here is nanosecond or not?
I believe it's nanosecond.
Okay. So I hope that answers your question, Lê Quốc Huy. Yeah. Yeah, go ahead, Tian. Sorry.
Okay, sorry about that. My kid boring me a little bit. Okay, so yeah, I think that's the old nanosecond. So you can see here, yeah, I mean the clock period is very long. So relatively, it's like if you have like 40 nanosecond, so you lose that like 5 or 4.5 nanosecond for the input to come. And then you have the rest, right? You have like 30 something for your data pad. Okay, so let me come back here, make sure I'm not. Okay, fast clock. Okay. So by looking at the constraint, you know how the clock defined, right? But once you already have the design, you don't want to go and look at the constraint. You can extract that information from the universe, right? So let's try that. We can do that here. Say, okay, I already have the design. I can see how the clock, define. So we do a report clock. So this should contain exactly the same information that we just looked at, right? So let's see here. Okay, so we have all the clock here, and you see the period. So we look at some of them have 40, right? The fast one is in my, clock 2x here is 4, right? And it tell you like, remember that zero, the 50% daily cycle, the leading edge and the trailing edge, right? So that's where it's rise and that's where it's fall, right? And all of these are non-generated clock. That means this is a clock defined at the port or pin. It's not, generated by something else for another clock, right? So if that's the case, then we have what I call a master clock and then the generated clock. So real design, we're gonna have many of those generated clock, right? You have a one master and then you have multiple generated clock later on. Okay. So I think that the key here is, I think, the timing report here. So, how do you know your design is, meeting the requirement, right? Timing wise, you do report timing, right? Uh, so report timing. The first time it's going to take a little bit of time to run. Okay, it's sorry, I have to look here. So let me. And you don't have to do this. If you have, you can write into a file, then you pull up in a text editor. It's just easier. I'll just call it. I just redirect into Pad 1, so I can pull up in my editor here. It's just a lot easier. So example 2. So I have this Pad 1 here. I can pull it here. For me, it's a lot easier. Okay. So I think I was asking whether the design is meeting timing or not. Obviously not, right? We have violated here, right? So we not meeting timing. I mean, we need to do some work here. But unfortunately, this is not the end. We just add import. So so that's the view. So if you look at the view, let's see here. I just want to see how things kind of like whole thing like connect together, right? So you look at the report, you say, what's this view come from, right? Remember the view definition file? So if I go here, I look at the functional max. Right here, create analysis view, name functional map, right? So this timing pad we're looking at here is for this functional map view, right? So in your design, you can have multiple, even hundreds of view, right? In this case, the timing violation is for this view only, right? If we're gonna do for this another view, I think that's a name, and I think we have only one view. Let's see. Okay, we're gonna try to do another view here. The timing gonna be different, right? So so this is func slow max. So we're gonna do func fast min. So let's do another one. You can do view. Okay, so that's another thing. I think you have to. Man, let me source it. I think it's had to be early. Let me try that. But I wanna show you is that in this analysis we have two view, right? One fast and one slow, right? So so in this way, in the pad one here we have is the slow one. We have that's my clock. And the clock, so my clock. So if you look at the constraint and you look at my clock, right here, create clock, my clock. The period is 8, right? So clock is 8. So that's how you can, sometimes you read the timing constraint and you have to go back. Timing report. I'm sorry. You look at the timing report. You have to come back to the constraint. You verify, right? Is that the intent? Is that clock defined correctly, right? So you just don't assume whatever you see in the timing report is correct. You have to verify, right? So that's it. So what it does is calculate, when the data arrive, and then say calculate the expected the arrival time, and then it's compare, right? If it's late, it's later than the expected time, then then you violate or you fail, right? If you come before, then you meet timing, right? So okay. Gotta make sure I cover everything that I have it in here first. Google timing. Okay, that's what work below that. So is the design meeting timing? No. What is the clock and its period? We did that. Is the report max or mean timing? We answered that, right? So this pad one is max. What did it do? The pad two. So you better look at pad two here. Oh. So I have pad one, pad two. So if I pull up pad two, it's going to be slightly different, right? So pad two, see the view, because I purposely did for a different view, right? You can see the pad one here. But yeah, the name is different because I do one, so I only pad one. But the view is Feng Slow Mac, right? This one, the pad two report here is Feng Fast Min, right? And this one is the IO, the default, right? So yeah, it just go from a clock to a pad. So what else I want to look at? What timing a pad? Okay, I think Phil, you mentioned this. What's the WNS, TNS, and FPE? So this is the worst negative slack, right? That means like the worst slack in the design. And this is the total negative slack, right? If you look at all the pad that has the negative slack, you sum them up, right? That's what you have. So, and this is how many of them, right? Failing, right? So failing endpoint, right? So, so let's see what else I wanna. So I think Phil, you did mention about the summary, right? So let's see. So let's say you want to do more than just timing report. And then you can do, let's say, do report. The thing is, you don't have to remember, right? You can just do help on.
Maybe report timing summary or something like that.
Right.
That's the last
So
one.
there's a lot, right? So we have report timing. Right? These are a little bit more advanced, right? But for today, we can do this. Okay. So because the last timing report was in early mode, that's why I only you only see the whole time, right? So, and that's what the worst negative slack is. They break it down, right, into different type of uh timing. So we have the asynchronous, we have the in to out. Essentially, it's just from the input directly to the output, right? And then we have rest to out, which is the flop clocking an output, right? And then the next one is into rest, which is the input coming in and captured by a flop. And the last one is from a flop captured by another flop, right? So it's breakdown. And so right now, is rest to out is the worst, right? So, but because we very early, we don't have the real clock yet, maybe the constraint is not correct, right? The latency maybe is skewed, right? Not correct. So early on, probably you want to look at this, rest to rest, because that independent of the clock latency, right? So that's the worst, and then the total, and then how many, right? So even though the rest to out is look very, very bad, but only 5 of them failing, right? But then rest to rest, even though it's only minus 413 picosecond, but look how many of them failing, right? So you have to look at two different things, right? You look at um, the worst and how of them failing, right? So and the sum of that is this number, right? So you look at all of that, and then so here it was saying that so they actually the good thing that they even tell you, right? So say, well, I want to look at the setup too. I don't want to just look at the whole, right? So by default, the tool only do setup or whole, right? To save the memory footprint. But sometimes you say, no, I want both. I want setup and whole at the same time. So you do that. Let's see, what is it? So even the constraint is not up to date. So whatever the document they have here is not up to date. That's legacy. So instead of set global with a common UI, you have to do the set DB. And now I do the same thing. Report timing summary. And then I expect to see both whole and setup. So it's rerunning timing right now, right? So okay. So it came back. So yeah, as expected, we have setup here. And then we have whole here, right? So because we force the tool to say, I want to do both, right? Calculate both timing, setup, and hold for me, right? So yeah, so we have some DIV here. Yeah, DIV, right? Yeah, we can look at that later. Essentially, it's failing MAC transition, right? Okay. Let's see what else we have. Okay. But sometimes you say, well, I don't want to just do the command. I want to see it, right? Say, well, there's a way you can see it too. So in here, you want to look at the report graphically, right? You go here, you do that's the timing menu. You do the debug timing. You go here, and so if you have the report, you can load the report, or you can generate a report, right? So for now, it just generated. So it's run, as you notice here, it's run the report timing. By default, it's going to run 10,000, and that's the report, right? All right. So And then it's going to load up into this GUI. You see. So this is the histogram, right? So the red one are the violation, right? So you look at between the red and the green, that's 0, right? So on the right, those are the pad that meeting timing, and the red one on the left up the 0 are the one that not meeting timing or failing timing, right? So by looking at this, say, wow, there's quite a few failing here, right? And then on the bottom here, they're gonna list by the slack, right? So the worst one on top, right? Just keep going down, right? Just so many of them know it's only up to 50, right? So and and the nice thing about this is you can actually zoom in here, right? So you can actually say, okay, I want to look at, if you zoom in here, so what are these one, right? So you double click on it. Oh, only one, right? One. So this is the worst one, and you can double click on that one. It's to tell you the full path, right? So tell you this is the time that launching, and that's the data path delay. So there's many tab here. You can have the data path, launch clocks, right? So to tell you capture clock, and even tell you, where's the constraint come from, right? It's actually tell you exactly where all the constraint come from. Is that awesome? Right. So to tell you that's how are the clock defined, right? All these clock uncertainty, right? So and then you can, nice thing is that you can look at schematic as well. Wow, look at this pad. So let's zoom in here. So this pad is, so this is the launch portion of it, right? So I believe this is the clock. Okay, so this is the pad, and then that's the clock coming in, and that's the flop, right? So your pad start from here, clock to Q, right? So this is the Q pin. As soon as you clock it, that's your Q pin. It's go to so many, right, states of logic, right? Just like that. And then it get captured, right? Look at this. It's so crazy. Just get captured by another flop, right? So this is the clock that capture it, and that's the data. Let's go to the, I believe that should be the D pin. Right. Right. When you click on this, it tell you right there, DFFD, right? So, and this one should be the CK. Right, CK pin, right? So let me zoom out. So your pad, the data pad, extremely long. You come in here, you clock it. So the one way to look at it is you have one cycle from this flop and to this flop, right? So as long as you have the delay, you sum up all the delay here, and then if it's less than one cycle, then you meet timing. If it takes longer than one cycle, then you fail timing, right? So uh, so that's the worst one. Say, well, let's look at some pad that actually meet timing. Say, okay, you can zoom in here, double click on that one. So we with this bucket we have 3, right? So okay, let's look at this pad here. So this is the data pad, right? It's launching from a flop, right? CK to Q here, that's the art, right? And it tell you what the cell is, what's the delay, right? The sum is just add up, right? One state after another, right? The first state, of course, is the same. So you hear the second state, it add the first one to the second one. You get that, right? So let's see, it's pretty long, and it's captured by another flop, right? And you can see here, right? So I think when I click here, it didn't relate. Oh, no. Okay, right here, right? So by just looking this, so this is the delays. So it's very even. You don't have something that stand out, right? Most of the delay is about the same, about 100 picosecond, right? So the first one, probably the biggest one here is your first flop, right? It's about 400 something picosecond. So this thing is really nice because you can quickly just scan this and say, wow, is there something wrong, right? If you see a big delay here, and maybe that cell is overloaded, right? It's just too small, have too much load, right? So by looking at this scan, that's fine, right? The timing look good. No wonder it's me timing, right? So look at schematic as well. Yeah, this one, right? It's very evenly. It's not too crazy as the first one. Okay, so I think I'm almost done. Let me see what else I want to show you. Let's look at a few more here. Oh, this has the memory. Let's look at that. So you come in here, go through the memory, and then go out, right? So it's the same thing. So I think this is launching. So we can data pad, right? So because go through the memory, you can see the big chunk right here. I believe this should be the memory, right? So yeah, let's see here. Make it long. So right. So the first one, you see the delay bar here. So about 80% of the delay due to this memory, right? And that's expected. The memory take a lot of time from read to write, right? So this case is, I think, it's a read, right? You read the data out of the memory. Of course, it's going to take some time, but right here, the delay bar is break everything down for you. It's pretty easy to look at. So the timing, just to get the timing out from the memory, it takes 2.2 nanosecond, right? Compared to everything else is 100 something, right? So but the sleeve look okay, right? So this GUI is pretty easy, Scott. If you know how to use it, it's a quick way to debug timing problem, right? So it's pretty useful. It's gonna take a lot of time to get used to it, but it's there. And this way is that essentially a histogram, right? It tell you how many failing, what's the worst one. Okay. Okay, so I'm gonna stop right here. I think that's all I have. And then I wanna hear from you. What's other question? Is there any question, Phil?
Yeah, I try to answer them with text, but I can read different questions, and then we can cover more if needed. So basically, TA Khánh Dương asks, why do we need um, MMMC, right? Why do we need it in general, and why we need it in Plagiarism specifically? What is multi MM and what is MC? How many modes are there in build design, and what we need to take care of them, like scan and ambis? What do we need to do?
Right, right. So I think you think of when you design a chip, right? You have a target performance, right? And you have a target say environment, right? Let's say if I design a chip for a car, right? So my requirement gonna be different, right? So I expect that chip to be inside the car, near the engine, right? So I said, wow. So I need to simulate that chip at, let's say, 125 or even 135 C, right? And then if you design a different chip for like indoor, or you even sells to some, northern country, they never get 135C. So it's like, no, I don't want to over design my chip for that environment, right? I don't need to simulate that corner of 135. 125 is good enough, right? So, and then the same thing, right? For a car that's going to be minus 40 40C, is that realistic, right? So if you use say an IO T chip, inside a market, right, then maybe you don't need it, right? Because it's more likely it's gonna be room temperature, right? And then you give it some margin. So the idea is that when you design your chip, your target, you know, target use for that one, right? How the customer going to use it, right? So that's why a multi-corner, right? And then within the same chip, right? Let's say functional, I expect people to do certain thing during functional, right? But let's say scan mode, the customer not going to scan my chip. Scan is purely for testing, right? So I have a different requirement during testing, right? So I don't need my test, my scan when I'm put the chip in scan mode. I don't need to run like super fast, right? It's not needed. It's purely for testing, right? So that's why we have multi-mode, multi-corner. It's is that you simulate the target environment that you want your chip to operate at, right? So if I'm in functional, I'm gonna simulate, right, extremely hot, extremely slow, and then extremely cold, extremely fast. So hopefully, with those two extreme conditions, I'm gonna be covered, right? But now with the new technology, you have to do more than that, right? Because you have to switch. Not sometimes you have the fast, and then later on you're going to learn about different VT, right? So they behave very different now. It's not like the old technology. So that's why in the new chip we have cross corner. We have like hundreds of view to simulate all those, different, environment, right? So the bottom line is you have to think how the chip going to operate, and then you try to simulate that, right? So because if you miss that, and then people are going to use in that unexpected environment, your chip going to fail, right? Because if your chip is not designed for minus 40C, then you take that chip, you put in a car, you drive to like the North Pole, it's not going to work because it's not designed for that.
Yeah. So I think people understand multi-mode I guess, better than multi-corner based on what I saw the questions asking back and forth. So I want to add to what Tian was saying, right? Scan mode and functional mode. For example, you have a chip that operates at 300 megahertz. In functional mode, you're doing DSP, etc. But in scan mode, you're testing your circuitry and you're running it at 10 megahertz only. So you would have two modes, scan mode where you feed in the clock at 10 megahertz, and functional mode, you feed in the clocks at the system clock at 300 megahertz. And you do your timing analysis and you're fixing them one mode at a time versus multi-mode. You define those two and you say, you tell the tool you are aware of these two, you do concurrent. The key is concurrent, right? Concurrent analysis, concurrent fixing, so you don't have to worry about fixing a timing problem in one mode that will mess up the timing problems in the other mode because they set the circuitry. So in the old days, we do one at a time, and then 10 years, 20 years ago, multi-corner, the tool become more sophisticated. They can do concurrent analysis and fixing. So that's good. So the latest question relate to why do we care about multi-corner, right? So we do care because multi-corner relate to process variation. As you know, it's not a single point that you're looking at. There are variations from one spot of the chip to the other in terms of delays, right? That relate to process variation, manufacturing, as well as operating temperature and operating voltages. There's so many different things. So you want to model all these extreme cases, and they mixing. Like for example, you have a case of fast N, a slow P transistor, all sort of complication. And if you don't define everything together and do concurrently, it's a nightmare to sign off timing for all different combinations. So that's why you need multi-corner, just defining everything and let the tool deal with the complexity.
Okay, thank you. I think there's another question about the I/O placement. I think I did mention about it. Look at it again here. So I think the question from Ngô Thái and How, right? I hope I say it right. So let's look at what we have here. So I think he's asking about if we have too many I/O. So let's say in this case, because this one is just a simple chip, right? So let's say we just look at this. So as of this point, the tool is expect with the logic that we have, the chip gonna be with the allocated side that we have, the chip gonna be at 84%, right? So okay, so what it means is that this when I place older cell, in theory, ideal is gonna come back with 84% utilization. That's a little bit high, but I think it's doable, right? And then you look at the pad, say, okay, so we do have space here. So it's not, in this case, it's not pad limited, but because of the utilization is at 84%, so more likely you cannot make the chip any smaller, right? Because if you make a chip smaller, to let's say, well, because you have space here, you can squeeze the chip smaller. No, because if you make a chip smaller, what happened? It's not going to be 84% anymore. It's going to be 90%, and that's just not realistic. You're not going to be able to route a chip, right? So in this case, so what if? Just what if you have what you have here is only 20%? That means we don't have a lot of logic, right? A lot of empty space here. And then we say, oh, if that's the case, then we can, eliminate all these spacing between the pad, right? And then you're gonna make the chip smaller to a point that there's no spacing between the pad. But then when you get to that point, you can't make it any smaller. So that's what they call a pad limited, right? So your chip size is determined by the pad that you have. And you can't just take a pad out or add a pad in, right? Because that's the function of your chip. You need that many I/O, right? So I
So
hope
the
I
question,
answered your question. Yeah, it's a
he went on to ask what are the solutions, right? If you have pad limited design, I think I answered it, but you might want to cover it.
okay. So I think we 5 minutes over. So
Okay.
If I can add a quick answer to that. So in case of the pad limit, so given a die area, you basically can estimate the maximum number of pad that can fit into that die area. But if in case you have design a chip that need extra I/O, so one of the solutions is that you design like dual row. Instead of having like one row of pad, you can have a second row, but that will increase the die size of the chip. So that is one of the solutions. And the other solution, of course, that you try to optimize the dimension of the pad. Like you try when you design a pad, you request the I/O designer to have the pad a little bit thinner. I mean the width is smaller, but increase the length a little bit. Again, that's also had an impact on the die area as well, but it's another option.
And the third option would be ball grid array, where you use the bumps, right, as IOs. So that's another option. And the dual ring is referred to as stagger pads because they're going to be staggered so that they can be bonded out.
Right.
Right. I mean, so when you have option for different packets, that's right. So, but most of the time you are limited to certain package already, right? Certain type of package. So
yeah, I have worked on pad limited design there was nothing. They just deal with low utilization. They tape out. So
yeah, usually for a simple design, it's more likely it's going to be pad limited. For the complex design, it's not going to be, right? So yeah.
Well, to our respect to those who have to make it to the next class. Thank you very much. If there are more questions, we can ask in the Google Classroom as well. All right. Thank you everyone for the question. I love them. Please keep them
Thank
coming.
you. All right. Thank you, everyone. Come on.
Recording stopped.
Cảm ơn mọi người.